Okay, so let's solve the Lewis structure for the third problem, which is HO3 minus. So if you look at closely here, it is a species with a negative charge. So it's a negative charge species, and this is actually known as a bicarbonate ion. You don't need to know the name, just a compound with the charges on it. And let's look at draw the Lewis structures. Okay. So the one thing to notice right in the beginning, you're going to need to write a Lewis structure with the negative signs on it, and that's the first thing to do to remember. And then let's go through the finding out the atoms. Hydrogens here, which is the first column. Carbons here, which is a fourth column. And then oxygens here, which is a sixth column. So then means the valence shell electrons in here, hydrogen is 1, and the carbon, there's a 1 carbon, so 4, there's 3, oxygen, which is a 6. So that is actually make it up to be the numbers, but one thing to remember, now we are dealing with a charged ion. So this is a number of valence shell electrons, right? So therefore, one negative charge means one extra electron, so plus 1 is going to be your number of valence shell electrons to be used to make bonds and the lone pair electrons. And so that will make it 24 electrons, okay? So therefore, now, once again, something that non-oxygen, non-hydrogen in the middle. So I'm going to put carbon here. And then the oxygen, there are 3 oxygens. So let me put an oxygen on top this time. And then hydrogen. Why don't I put hydrogen on here? So, okay, so I just kind of arrange the atoms. And first thing to do is 1, 2, 3, 4. So I'm going to use 4. So 24 minus 8 electrons, so that will be 16 electrons. And then I'm going to put the necessary oxygen. So oxygen, the single bond, you need 3 lone pairs to satisfy the octet rule. And so this is, you need 2 lone pairs, those with 2 bonds, the oxygen with 2 bonds. So I'm going to put it just like that. So see how much electron you have used. So far you have used 12, 14, and 16. So I guess you're done using it. So the 12, 14, and 16. So this is a bonds. And then 16 electron left over. I mean, that's 8 electron from the bonds, and left over, you're using 16 electron for lone pair electrons, and you have no electron, right? Nothing for the atom in the center. So, and then we'll do the same practice before. I explained it before that the former charges of this oxygen is -1, this oxygen is -1, this is 0. And that's also former charge is 0. And if you look at the one in the middle, the summation of all the former charges on the atom in this molecule should be the same as former charges, which is a -1. So therefore, this former charges must be +1. So that's one of the shortcut way that I love to do it, because that's the easiest one to do. But once more, I'm going to do it here. Former charges of carbon is 4. Carbon is 4 in the valence shell electron, minus number of lone pair electron, 0. And half of bonded electron, there are 3 bonds, so 6 electrons. So 4 minus 3 is +1. So that's why it should have these charges. Former charges of 1. And then once again, if you now start to notice that, let me use different colors. If you look at let's look at this this kind of interaction. You have negative charges here, positive charges here. Even this one does not, carbon does not satisfy the octet rule. So all they need to do is, let's make everyone happy by saying, why don't I share extra lone pair in a form of a bond so they can form the double bond. And by doing so, this one, the former charges are gone by forming double bonds. So no former charges. And the carbon is here. And this one is right there. And then OH. So that's the right form of the former charges. And then this one is now all of no former charges here. So let me try to do the former charges in different colors. So let's do the former charges. This one is now no former charges, no former charges, no former charges, no former charges. But this one still retain their former charges. So that's why the overall negative charges. So what this one is saying to us is HCO3 minus ion is actually one of the oxygens, this one, maybe this one, or in the same logic, it can be this one if you have this one is double bond on the other side. So we can think about doing about this. The charges, negative charges is localized is one of the oxygens here. So because of that, I can actually think about the other way. Why don't I make this one forming a double bond? By doing so, this carbon has too much electrons, so this one can push and to give an electron back to this. So so by doing so, you can think about the following consequences. So let me rewrite in a more neat way. You used to have so in the drawing above, it looks like this. The former charges is localized on the one on the top, but now the lone pair electrons, so this lone pair can form the double bond, but by forming the double bond, carbon has a 10 electrons, so they cannot take it. So they're going to push this one back to the other oxygens. By doing so, you will have this scenario of the oxygen, carbon, and they form double bond with two lone pairs. So now the minus charges develop here, and then oxygen and the hydrogen. Okay, so this is what is called the resonance structures of this bond known as COO bond. Okay, so this one has those kind of the nature of making this charge delocalization. So if you go to the organic chemistry in your sophomore class, your instructors likely to write actually charge delocalization this way. This is quite well known. This is much more close to the stereochemistry, but because let me tell you right now here, right? Because of the double bond nature, we will learn this. This one is sp2 hybrid orbital carbon, whereas this one has sp3 hybrid, which is a tetrahedral, and this is the square, not square, planar triangle. That's something that you will learn. They are on this essentially triangle-like shapes. You will learn it later in the future. But for the answer that they are looking for here, is the correct answer is essentially this one. Okay? If you can write the resonance structures, that will be the one, and then the sort of the advanced form of writing it is you kind of write a spreading of charges just looks like that. Okay, thank you for your attention.